Welcome back to Clearbook Geometry. This is section 10.5, Surface Area of Pyramids and Cones. The objectives of this lesson will be to learn and apply the formulas for lateral and total surface area of pyramids and cones. Let's get started. First, we're going to go over some vocabulary associated with pyramids. The vertex of a pyramid is the point opposite the base of a pyramid. A regular pyramid is a pyramid whose base is a regular polygon and whose lateral faces are congruent isosceles triangles. Okay, so in this regular pyramid shown here, the base is a regular polygon. In this case, it's a hexagon. It means all the sides are congruent, and all of the lateral sides come up to the vertex, so they are all the same height. They all have the same base, and they are all congruent isosceles triangles. The slant height of a regular pyramid is the distance from the vertex to the midpoint of an edge of the base. So the slant height here runs from the vertex all the way down the side to the edge of the base. The altitude of a pyramid is the segment from the vertex to the plane of the base, and that it's perpendicular to the plane of the base. Okay, so for the altitude of a regular pyramid, it's going to go from the vertex, and it's going to go straight down to the base, and it's going to be perpendicular to that base. In this pyramid, it would go straight down to the plane that contains the base and be perpendicular to that plane. So this blue segment is the altitude of the pyramid, what we would call the height of the pyramid, and this orange line is the slant height. Okay, we're going to learn how to find the surface area of regular pyramids. We're going to start with the lateral area. The lateral area of a regular pyramid with perimeter P and slant height L is equal to 1/2 times the perimeter times the slant height. Okay, we can also write this as perimeter times the slant height divided by 2. Okay, the lateral area, what we're doing is finding the area of each of these sides that run from the vertex to the base. The area of each of these triangles. These are called the lateral faces, so the area of all of those added together would be the lateral area. To find the total surface area, we're going to use the lateral surface area plus the area of that base. That would give us the total surface area of all the surfaces of this pyramid. Remember, this big B represents the area of the base. Example 1 says to find the lateral and total surface area of the regular pyramid. Let's go ahead and start with the lateral area. I'm going to label that as LA, so I know we're talking about lateral area. And the formula is the perimeter times the slant height divided by 2. I can see that the base of this pyramid is a hexagon with 6 sides, and I know that it's a regular pyramid, so all of those sides are congruent. So the perimeter of that base is going to be 48 centimeters. And they give me the slant height, so I can find the lateral area using that formula, 48 times 12 divided by 2. And we get 288 square centimeters. Okay, now let's look at the total surface area. That formula uses the lateral surface area plus the area of the base. So I know that the lateral area is 288. So this can be plugged in right here. So we have S equals 288 square centimeters plus the area of the base. So I've got to figure out what the area of the base is. So looking at my base, it is a regular hexagon, so all the sides are 8 centimeters long. And I need to find the area of that. Well, you may remember that the area is the apothem times the perimeter divided by 2. So I know the perimeter, we said it was 48. So now I need to know what the apothem is. So you may recall that the apothem is the length of the segment that goes from the center to the edge that's perpendicular to the edge. That's the apothem. We want to find that distance. So we create this right triangle and use the central angle. Remember, 360 degrees, we divide it by 6. That gives us 60 degrees, but we only used half of it, and this is this angle right here, 30 degrees. So since it's a right triangle and I have a 30-degree angle, that gives me a 30, 60, 90 triangle. I know that the short leg is going to be 4 centimeters. You can use special right triangles, or you can use trig to find the length of A. I know that if the short leg is 4 centimeters, then the long leg is going to be that times the square root of 3. 4 times the square root of 3 times 48 centimeters divided by 2 gives us a base area, or a big B, that's equal to 166.277. So now I can go and plug that back in, and I get 454.28 square centimeters. For example 2, we're given that the base edge and the slant height of a regular square pyramid are both multiplied by a third. We're going to describe the effect on the surface area. Okay, we've done this before in Unit 9 when we were talking about two-dimensional figures, the change that occurred to the area when we changed dimensions. So this is really the same thing. We're going to look at the original surface area. We're going to change those units and look at the new surface area and see how those compare. Okay, so for the original, I have a slant height of 12, and I have a side length of 15. And they tell me it is a square, so I know the perimeter is, which is 60. Okay, so when I put that into my formula, I end up with this surface area of 585 square feet. Okay, well, if I change my edge and my slant height by multiplying it by a third, so instead of having 12, I have 4 for my slant height, and instead of having 15, I now have 5 for my edge. When I put that into the formula, I end up with a surface area of 65 square feet. So remember, when we're trying to compare them, we always put the new over the old. So I get 65 over 585, and if you reduce that, you end up with 1/9. So when we change to all the dimensions by 1/3, because we multiply those together to find the area, we take that change and we square it. So we end up with 1/3 squared, which is 1/9. Okay, now we're going to take a look at cones. They're very similar to pyramids, just that the base is now circle. The vertex of the cone is the point that's opposite the base of the cone. The axis of the cone is a segment with endpoints at the vertex and at the center of the base. A right cone is a cone whose axis is perpendicular to the base, and an oblique cone is a cone whose axis is not perpendicular to the base. So you can tell it looks like it's slanted here, where the right cone is perpendicular straight up from the base. Okay, the slant height of a right cone is the distance from the vertex to the point on the edge of the base. Just like in a pyramid, it runs along the lateral surface of the cone from the vertex to the edge. The altitude of a cone is the segment from the vertex that's perpendicular to the plane that includes the base. So in this case, from the vertex straight down perpendicular to the circular base would be our altitude. It's also what we call the height of the cone. Now we're going to talk about finding the surface area of a right cone. First, we'll look at the lateral area. The lateral area is found by using pi times the radius of the base times the slant height. The total surface area would be that same lateral area, but then we're going to add in the area of the base, just like with the pyramid. the base is always a circle. It never changes, so it's always pi r squared. In example 3, we're going to find the lateral and total surface area of the cone. Okay, let's start with the lateral surface area. That formula is pi times the radius times the slant height. In our drawing, we're not given the slant height, but we are given the altitude. As you can see, the altitude, the slant height, and the radius of the base form a right triangle. So if you have two sides, you can find a third by either using Pythagorean theorem or the fact that this is going to be a Pythagorean triple. The side lengths are 8 and 15. The hypotenuse will always be 17. But if you don't recognize that, you can always use Pythagorean theorem to find that out. Now that we know the slant height, we can use our formula, which is 136 pi square inches. This would be our lateral area. If we rounded it to the nearest hundredth, we would have 427.26 square inches. Okay, now we can find our total surface area, which is the same as the lateral, plus the area of the base, which is always pi r squared. Okay, so I can take what I found from my lateral and put it in there, plus pi times 8 squared. We get 200 pi square inches, which is approximately 628.32 square inches. One last example, we're going to find the surface area of a composite figure. Remember, a composite figure is several simple shapes put together to form some complex shape. But knowing the surface area formulas for cones, we can easily find the surface area of this composite because it is two cones put together. And the way these are put together, they're put together at their bases, so their bases are no longer a surface of the figure. So we really have the lateral surface area of this cone plus the lateral area of this cone. So I'm going to call these cone 1 and cone 2 and find the lateral area of both of those. The surface area will be the lateral area of cone 1 plus the lateral area of cone 2. Remember that the lateral area formula is pi RL. Okay, so let's do that for cone 1. I'm given that my slant height is 12. I know the radius is 6, so I have all the information I need. I have 72 pi square inches for that one. For cone 2, I use the same formula, but my radius is the same, but my slant height is going to be different. They didn't give me the slant height, but they did tell me that the altitude is 8. So again, if you can recognize that this is a multiple of a 3, 4, 5 triangle, you would recognize that if this is 6 and the other leg is 8, then the hypotenuse would have to be 10. If not, you can do Pythagorean theorem and find it that way. So once I find the slant height of that cone, I can plug it in. The lateral area of the second cone is going to be 60 times pi square inches. So now that I know both pieces, I know that the surface area will be 72 pi plus 60 pi, which is 132 pi inches squared. If we wanted to round that to the nearest hundredth, we get 414.69 square inches. And that's it. If you want to see some more examples, please look into your textbook, pages 689 through 692. And there's also some more practice problems you can do, starting on page 693, where you can work the odd problems, and the answers are in the back of the textbook. And as always, please come to class tomorrow with any questions that you have on any of these examples. See you then.